Morning, everyone. Today we're going to take a quick look at a PowerPoint on statistics. We're going to be studying statistics and probability, so hopefully you'll find some of this helpful as we move forward. Today, as you see here, we define statistics as the collection, evaluation, interpretation of data. I'm sure you all have some experience with statistics. You've calculated averages or mean, maybe even median and mode, or standard deviation. And so this may be a review for some of you, and that's okay. But yeah, I mean, we'll see how familiar you are with this as we go through. There are two different types of statistics. There's what we call descriptive statistics, which describes collected data, and then inferential statistics generalize and evaluate a population based on sample data. In other words, with inferential statistics, if I examine a subset of the population, say a few thousand people, then I might be able to generalize based off of what I find with those few thousand people. I might be able to make generalization statements about the entire population, and so that's what we call inferential statistics. This is different than descriptive statistics, which might be very specific to a given population and only describes that population. Data can be categorical or qualitative. Values that possess names or labels could be the color of M&Ms, breeds of dogs, any sort of property that can't be measured with numbers is what we call categorical or qualitative data, whereas we have something else called numerical or quantitative data, and that's of course values that are numerical. We can calculate them. We can run the numbers, so to speak. Okay, so that could be population, the numbers of M&Ms, the height of people, number of defective parts. It could be all sorts of different things, weights. But the point is, sometimes you'll have categorical data which describes things in terms of a name or an age, whatever it might be, versus something that we can calculate and or measure. So we have different ways to sample when we're collecting data. You can do a random sample. You can do systematic, stratified, cluster, convenience. These are all different ways of labeling sort of how we get our data. And this becomes really important when you're trying to make generalizations. So we talk about inferential statistics. This is really important. If you want to, for example, try to generalize your information to the population, it's very important to understand if you have a random sample or not. Sometimes you might feel like you have a random sample, you might think you have a random sample, but you don't. For example, if I send out a survey to 1,000 people and I want to collect data about the personality types of these people, and then I get, say, 422 responses, I might try to generalize that data from those 422 responses, and I'll say, well, that's a random sample. But it's actually not random because it was an optional survey, and those 422 people chose to respond, whereas the other 500 something did not. And that is important because that means that those 422 have a certain personality trait or characteristic that makes them obviously more likely to respond to a survey. And so they're already a self-selected group. So you have to be very careful about the way in which you try to generalize and an understanding of what your sample represents. Because even sometimes when you think you have a random sample of people, you don't. And so what I just talked about, this idea of survey, might be what you call a convenience sample. In other words, I sampled the people I surveyed the people I could, and then those who felt like responding or could respond did. And that was very convenient for me because it was what I had access to, right? But then those people also, again, self-selected. So that's very important to keep in mind. You cannot generalize unless you have a truly random sample, which is a very difficult thing to ensure sometimes. Graphical data representation here. You guys hopefully have heard of a histogram. Histogram is a very useful way to visualize data, and it's what we call a frequency distribution graph. And frequency means it really is just telling us how often things occur, or how many people in a sample have a certain property here. Okay, so excuse me. If we look here, frequency polygons, these are similar to histograms, but they're just drawn a little bit differently. And then bar charts, categorical data graph is usually used for what a bar chart is used for. In other words, down here you'll have like numbers, and over here you'll have a descriptor such as, the color, or perhaps the race, or the any other sort of descriptor of a person or sample of people or objects that you're measuring. Okay, so that oftentimes bar charts are used for categorical data graph. In other words, we can't necessarily measure this numerically, but we can put a label on the y-axis here, and so we'll just tell how many. And then a pie chart is another categorical graph. It's just a different way of representing similar information. So I'm sure you guys are all familiar with pie chart. All right, so we're getting into some review here about the specific calculations you can make with statistics. It says here mean, which we call the arithmetic average, which we have surely seen before. Just to review, is equal to the sum of all of the values divided by the number of those values. Okay, so if you want to know the test grades in a particular class, say you have 20 students. Well, what you're going to do is you're going to add up all of those test grades, and then you're going to divide by 20 to find the average test grade for that class. Or perhaps you yourself have had 5 tests in a class, and you want to know what your test average grade is. So what you're going to do is you're going to add up the scores of all 5 of your tests, and you're going to divide by 5. And that's just a very simple calculation for arithmetic mean. And it's certainly very frequently used. And the whole idea for mean is it's a measure of central tendency. And so there are several of these ways of calculating with statistics that are centered around the idea of central tendency. In other words, what do numbers have in common in this data set? Keep in mind that mean is very strongly influenced by outliers, which are very large or small values. So for example, if I have a test and I look at my average test grade, it might be 68%. And I say, oh, that's not very good, right? Man, I didn't do a great job teaching this unit. But then I look at the numbers and I remember, oh yeah, that student got a 0 for cheating. Well, that 0 is going to very heavily influence the data. And so if I take that 0 out, maybe my test average jumps to a 78 instead of a 68. And I say, oh, well, I didn't do too bad teaching that after all. That one outlier strongly influenced my arithmetic average or mean. So here we could see an example for determining the mean value. We have these numbers right here. How many are there? Well, there's a total of 5 right there, and then 6, 7, 8, 9, 10, 11 numbers. So how do we calculate the mean? Of course, we're just going to add those up and divide by the total number, which is 11. And once again, we'll get 524 over 11, which comes out to about 47.64. So a very quick example there for a calculation of mean. Median's a bit different. It says data values that divides a data array into 2 equal groups. In other words, the median is like, well, let's find the very middle of your data and draw a line through it, is the general idea. Okay? Data values must be ordered from lowest to highest in order to figure out what the median is. And this is useful in situations with skewed data and outliers. So if you have that situation with a test, then a median might be a better way to understand my students' grades than the mean or the average. So let's take a look here. So if we want to figure out the median, the first thing we have to do is reorder the data set from lowest to highest. So we do that. And once we've done that, then we can go ahead and look at the median. It says here, select the data value that splits the data set evenly. So in this case, the middle value is 58. And so our median is, for this data set, 58. Okay, so there's no, in this example, there's no calculation where you have to do anything in particular. On the other hand, that could change if you have an even number. Notice we had 11 values for this data set. If we have 11 values, we're going to have 1 in the middle, and that was 58 here. But yeah, if you only have 10, then things change a bit. So here we see the data set with one of our values missing, 2 is missing. And if that's the case, then what we have to do is we have to look at the central two numbers, and we have to take the average of those two numbers in order to calculate the median. Mode is most frequently occurring response, is the most frequent occurring response within a data array or a data set. In other words, the mode is the number that happens the most frequently, the most often. It says here it's usually the highest point of a curve. If you're thinking about a bell curve, mode is usually there. It may not be typical for the data set, but it did happen to be the most common. And sometimes, yeah, you won't have a mode at all because, in a class of 20 kids, it's not always going to be the case that 3 kids got the same score. Sometimes everybody has their own unique score, so that all depends. So modal, bimodal, multimodal, there could be multiple different modes in a given data set. You could have, for example, if I have a test that I administered to students, maybe 3 of those students got 100s and 3 of those students got 80s. So I'm going to have a bimodal data set because I'm going to have more than one mode. Also, it's important to go back to this idea that it's not necessarily typical. So, for example, a score of a 100 is not that uncommon on a test. So I might give a test and I might have 2 100s, but I might have everybody else in the class in the 70s or below. And so that's not necessarily to say the mode then represents what is typical in that class. In fact, the mode was the outliers, but nevertheless, it's the most common value, so it is by definition the mode. So here we're going to determine the mode of our data set. So it's just looking for common values. So we see 63 is duplicated, no other numbers are duplicated, so the mode is 63. Very simple. Now if we look here, if we look at this data set, we could look to see if we have common values, and I'll give you guys just a second there, right? And once again, this time we have 63, but we also have 59 as a common value as well. So this is a bimodal data set because we have 2 modes, so bimodal. And then if we look here, just looking for common values, we might see 63, we see 59, and we see 48. And so therefore, in this case, we have a multimodal data set because we have 3 different modes. All right, data variation. How can data vary? Well, the scatter of that data might be called the range, and it's the difference between the highest and lowest values. So the range of the data has to do with, how far apart are what's your spread of the data? How far apart are your highest and lowest values? Standard deviation is a bit different and probably more useful. It's this, by definition, it's the square root of the variance. So of course we have to understand what variance is. But we're going to get back to that in just a moment. Let's talk about range for just a moment. So if we look here, it says calculate by subtracting the lowest value from the highest value for the range. And that's very simple. So if we go back to our good old data set that we've been working with here, we see the highest value is 63 and the lowest value is 2. So if we subtract those 2, we get a range of 61, and very simple. Standard deviation, boy, is this slide complicated, right? So let's take a look here. There's a couple different types of standard deviation. As you can see here, we have sample standard deviation and population standard deviation, okay? In practice, only the sample standard deviation can be measured and therefore is more useful for applications, okay? So population standard deviation is sort of part of that inferential statistics. It's you can never directly measure population standard deviation. Sample standard deviation is much more commonly used. If we look at the definition for that, it says a standard deviation of a sample estimates the standard deviation of a population based on a random sample. The sample standard deviation, unlike the population standard, is a statistics that measures the dispersion of the data around the sample mean. And this is very important. In other words, we know that any data set is always centered around a mean value, right? And what standard deviation seeks to do is to try to understand how far away from that mean value my values are on average. In other words, if I have a mean of 50, how far away, if I picked a random number from that data set, how far away from 50 is that random number going to be on average. And that's effectively what standard deviation is. The higher the standard deviation, the more diverse the data set is, and the lower the standard deviation, the more uniform it is. So if I have a standard deviation of 0.5 with a mean of 50, then on average, I'm going to have numbers that are very close to 50, 51, 52, 50.3, 50.8, 52.6, 51.9, etc. And on the other hand, if I have a standard deviation that's 20 and my mean is 50, then I'm going to have a much larger range for my data set. I might have 75, 49, 37, 57, and all these different numbers that are centered around 50, but they're much farther apart, much farther away from 50 on average. So a small standard deviation says these numbers are very tightly packed in around the mean, whereas a large standard deviation tells us that the numbers are sort of diverse and spread out around that mean. So if we look at sample standard deviation, we can sort of break down the formula here. S stands for sample in this case, and first thing you would have to do to calculate the standard deviation is calculate your mean, which is x bar right here. And if you look there, that's where we have our mean. Now x is any data value, so it says here subtract the mean from each data value and then square it, and then you're going to add up all of those values. So there's actually a lot of different calculations going on right up here in the numerator, okay? If you have 10 data points, you'll have one mean, but you'll have to subtract from each data point the mean, and you'll have to square that difference. And then you'll have to do that 10 different times, and you'll have to add up those numbers, okay? So that's actually kind of like a tedious process. So for this reason, a lot of times computers are used and calculators are used to calculate standard deviation because it is a tedious process. Now, if you had a sample of 10, you'd have to do this 10 different times in order to calculate your standard deviation. This subtraction and squaring process 10 times. However, if you had 1,000 data points, then you would have to do that calculation 1,000 times, and you can imagine how just absurdly ridiculous this becomes as you get into larger and larger numbers. You know, if you start measuring populations from a census where you're talking about hundreds of millions of people, it's completely impractical to try to do this calculation by hand, and this is where computers really come in handy. So do understand that there's a lot going on in the numerator. It's each data point minus the mean squared, and then you do that for every single point, and then you add all of that up. That's what this summation symbol right here, sigma, means. And then you're going to divide that by n minus 1. Well, what's n? N is, of course, the number of data points you have. So for a data set of 10, n is going to be 10, and then you subtract 1, so it's 10 minus 1 is 9. And then you're going to take that and divide the numerator by 9, and you're going to take the square root of that in order to calculate your standard deviation. So here's an example of calculating standard deviation. We have a total of 10 data points here, and we can then do what we need to do, right? So we're going to first calculate the average, and we add up all of those. By the way, I've just noticed here we have an S instead of a sigma there. That's probably a mistake, so I don't know where that's coming from, but just keep in mind this S right here should be a sigma. So that just means we're adding up all of our X values. So we add up all these numbers, we divide by 11, we get our mean, right? That's easy. Now it says here, let's go ahead and calculate X minus X bar squared. And remember, we have how many points in this data set? We have 11. So we're going to have to do step 2 11 times, okay? So here's sort of like a brief rundown of what that ends up looking like. As you can see, here the numbers start off large because they are far away. 2 and 5 are very far away from the mean. But when we get to numbers like 48 and 49, they're very close to the mean, so the difference is very small even when you square it because, of course, they're very close, and the standard deviation is a measure of how far away from the mean. Anyway, you continue to do this. You have a total of 11 calculations. Like I said, there's quite a few calculations, and you now have your standard deviation's numerator in this little fraction when you add up all of these numbers. So at step 2, all we've done is we've subtracted and squared all 11 numbers from that mean there. Then in step 4, suddenly they jump to, okay. So there's a few errors here, guys. Sorry about that. So this is, again, a summation symbol. In step 4, you're going to add up all of these numbers that you just calculated. So here are all the numbers that we just calculated. We're going to add those all up. That becomes our numerator up here, and it comes out to 5,024.55. We're going to now divide that by n minus 1, n being 11. Therefore, we're dividing this guy by 11 minus 1, or 10. And if we do that, we get 502.46. And that's under a radical. So in order to calculate our standard deviation, we actually have to take this number, 502.46, and we have to take the square root of that number, and then we get a standard deviation of 22. And so what that number means, once again, that standard deviation of 22, the mean is 48 in this data set. If I were to pick a random number from this data set, I would expect on average to be about 22 values away from the mean. So if I pick 63, I'm going to be 15 points away from 48. If I pick 5, I'm going to be a larger number, 43 points away from 48. But the average is going to be about 22, and that's where that meaning comes in, what standard deviation actually does. This example here is calculating the population standard deviation. Calculating the actual mean here, yeah, that's the hard part of this. But in any case, you can go ahead and see how this works. We're going to go ahead and do the same kind of thing, and we get the same average. So with standard deviation of a population, the only difference you'll notice in this formula compared to the previous formula is instead of n minus 1 in the denominator, we have n. And that's just going to change our calculation a little bit. Instead of dividing by 10 like we did in the previous part, we're just going to divide by 11. And that's basically the only difference here. So we go through and we calculate these guys all over again. Of course, you don't actually have to calculate them again for the same data set because we already have those numbers. You're going to add them all up, which is what we see here. Then you're going to divide by 11 instead of dividing by 10, and you'll see that your number comes out to 456.7769. Take the square root of that guy, and you have a standard deviation a little bit different. So the population standard deviation only a little bit lower than the sample standard deviation. And then we're almost done, guys. This is just quickly taking a look at graphing frequency distributions. So this is giving an example of a coin toss. Assign the variable x to represent the frequency of heads occurring in each toss, okay? So what they're looking at here is if we toss a coin 3 times, what is the outcome of our experiment? So this is kind of showing you the different possibilities, right? So if you think about it, when you throw a coin 3 times, this is every possible outcome from that experiment, right? So you can start varying it. Okay, it's either going to be heads, 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 or heads, heads, tails, or heads, tails, heads, or tails, heads, heads, and then you go through all the options. Now, x is the frequency of heads occurring in each toss. And so we can look here and we see that we have 3 heads occurring. Here we're going to have 2, we're going to have 2, we're going to have 2, we're going to have 1, 1, 1, and 0, right? And so here's every outcome from that experiment, and then we just went ahead and assigned our x values, right? So what we're going to be doing then is creating a graph of this data. That's essentially all we're worried about, and this is a frequency distribution graph. So x equals 1 when these 3 scenarios occur, and so we can calculate the likelihood that an outcome variable will occur within an experiment, and this is looking at probability here, right? So what is the probability that we're going to get heads, essentially? And so what we can do here is take a look, and when we have a frequency of 1, right, we have a 3/8 probability. When we have a frequency of 0, we have a 1/8 probability, because there are a total of 8 outcomes, and there are 3 numbers where we have a 1, and there's a 0 only once, so that's a 1 out of 8 opportunity, 3 out of 8 opportunity. What's 2 going to be? Well, that's going to be 3 out of 8 again, and 3 will be 1 out of 8 again. And of course, you know if you've done this correctly, because you add all of these up, you should get a total of 1, or 8 out of 8. And in fact, we do. 1 and 3 is 4, and 4 is going to give us 8 out of 8. So we can then use this to create a histogram. And the histogram right here is one we saw on an early slide, but now it makes some sense to us, hopefully. But the general idea is you can look at the different frequencies for heads over here. How many, when we have 0 heads, how often is that going to happen? When we have 1 head, how often? When we have 2 heads, how often? And when we have 3 heads. And we can start to plot that. We have 0, 1, 2, and 3 for our x-axis here. And then we have our probabilities on our y-axis. And our histogram ends up looking like this. We have 0, 1, 2, and 3, and we can see those relative frequencies. And again, the total here for the fractions adds up to 8 out of 8. Okay, and this is an example of available airline passenger seats 1 week before departure, right? So this gives us an idea of how often this occurs, so percentage of the time, and then this is number of open seats. So we can see that airlines tend to want to really load up their aircraft as much as possible, and you know numbers like having 12, 11, 10, 9 empty seats are pretty infrequent. You can see this is a very low probability. These are like 1, 2, 3% probabilities, and then much more common is anywhere from 1 to 5 open seats. With 5 being our most common number of open seats, over about 12% it looks like. And so this kind of just gives you, again, an understanding of the relative frequency that these number of open seats come up. And of course, if I add up all of these different numbers here on my y-axis, 3%, 5%, 7%, 9%, 12%, etc., I should get a total of 1, or in this case like 100%, because that would be the total number of times an airline has that. So it kind of gives you, it kind of gives you an understanding of how histograms work there. Okay, guys, I know that was a bit long, so hang in there. I will have your assignment posted soon, and I hope you have a lovely Monday. Take care.